For centuries, humanity has wondered whether Earth is the only world capable of supporting life. Every civilization has looked toward the stars and asked the same timeless question. Are we alone? Today, that question is no longer confined to philosophy. It has become one of the greatest scientific investigations in history. At the center of that search lies a small rocky planet orbiting the closest star to our own. Its name is Proxima b. Located approximately 4.2 light-years from Earth, Proxima b circles the red dwarf star Proxima Centauri, the nearest stellar neighbor to our solar system. Although astronomically close, reaching it with today's spacecraft would still require tens of thousands of years. Yet despite the immense distance, this distant world has become one of the most intriguing destinations in modern astronomy. The reason is surprisingly simple. Proxima b orbits within what astronomers call the habitable zone, the region around a star where temperatures may allow liquid water to exist on a planet's surface under the right conditions. Since liquid water is considered one of the essential ingredients for life as we know it, the discovery immediately attracted worldwide attention. But being inside the habitable zone is only the beginning of the story. Unlike our peaceful Sun, Proxima Centauri is a red dwarf, a much smaller star that behaves in dramatically different ways. Although it produces less light than the Sun, it is highly active. Without warning, it unleashes enormous stellar flares capable of releasing powerful bursts of ultraviolet radiation and energetic particles into surrounding space. Because Proxima b orbits extremely close to its star, completing an entire year in only about 11 Earth days, it experiences these outbursts far more intensely than Earth experiences solar storms. This raises one of astronomy's biggest questions. Could a planet survive under such relentless bombardment? The answer depends on something scientists have not yet confirmed: its atmosphere. If Proxima b possesses a dense atmosphere along with a strong magnetic field, it may be capable of protecting its surface from much of the incoming radiation. Just as Earth's magnetic field shields us from harmful solar particles, a similar protective barrier could help preserve water and create conditions suitable for life. Without that protection, however, billions of years of stellar activity might gradually strip the atmosphere away, leaving behind a dry and barren world. Another fascinating possibility involves the planet's rotation. Many astronomers believe Proxima b could be tidally locked. This means one side of the planet permanently faces its star while the opposite side remains in endless darkness. At first glance, such a world seems hostile. One hemisphere would endure constant daylight and intense heating. The other would remain frozen beneath an eternal night. Yet computer simulations suggest reality may be more complicated. Between these two extremes lies a narrow region where daylight slowly fades into darkness. Scientists call this the terminator zone. If an atmosphere exists, winds could transport heat from the hot side to the cold side, creating a band of moderate temperatures. Within this twilight region, liquid water might remain stable for long periods. Instead of deserts or frozen wastelands, there could be lakes, clouds, and weather unlike anything found in our solar system. Such environments remain entirely theoretical. But they are scientifically plausible. That possibility alone makes Proxima b one of the most exciting worlds ever discovered. Studying such a distant planet is far from easy. Unlike many exoplanets discovered by astronomers, Proxima b does not regularly pass in front of its star from Earth's perspective. This means scientists cannot easily analyze starlight filtering through its atmosphere using the transit method. Instead, researchers must rely on indirect observations, sophisticated computer models, and increasingly powerful telescopes. This is where the James Webb Space Telescope enters the story. Although Webb cannot directly photograph Proxima b, Its extraordinary infrared instruments allow astronomers to study nearby planetary systems with unprecedented sensitivity. Together with next-generation observatories such as the extremely large telescope, currently under construction in Chile, scientists hope to detect faint signals revealing the planet's atmosphere, temperature, and perhaps even the composition of its surface. Every improvement in telescope technology brings us one step closer to answering a question that has fascinated humanity for generations. Is Proxima b simply another rocky planet? The search for life on Proxima b does not end with finding a rocky planet inside the habitable zone. In many ways, that discovery was only the beginning. The next challenge is determining whether this distant world has the ingredients needed to remain habitable over billions of years. For astronomers, the most valuable clues come from something almost invisible: light. Every beam of light carries information about the object that produced it. By separating light into its individual wavelengths, a technique known as spectroscopy, scientists can identify the chemical fingerprints of distant worlds. This method has already transformed our understanding of exoplanets. The James Webb Space Telescope has successfully detected molecules such as water vapor, carbon dioxide, methane, and carbon monoxide in the atmospheres of several distant planets. Each detection demonstrates that studying the chemistry of alien worlds is no longer science fiction. It is becoming routine astronomy. Although Proxima b cannot currently be studied in the same way because it does not transit its star from Earth's perspective, future telescopes may eventually detect faint light reflected from its surface or atmosphere. Even a small amount of reflected light could reveal extraordinary details. Scientists could estimate surface temperatures, search for clouds, measure atmospheric pressure, and perhaps identify gases that indicate active geological or biological processes. Of course, discovering a single molecule would never be enough to claim life exists. Nature often produces the same chemicals through completely different processes. Methane, for example, can be released by living organisms, but it can also form through volcanic activity or chemical reactions deep underground. That is why astronomers look for combinations of gases that are difficult to explain through geology alone. The search is careful, methodical, and based entirely on evidence. Meanwhile, researchers continue learning from some of Earth's most remarkable organisms. Deep beneath the oceans, around hydrothermal vents where sunlight never reaches, entire ecosystems survive using chemical energy instead of photosynthesis. Elsewhere, microscopic life thrives inside acidic lakes, beneath Antarctic ice, and within rocks exposed to intense radiation. These extremophiles have fundamentally changed biology. They demonstrate that life can adapt to environments once considered completely uninhabitable. If organisms on Earth can survive such extremes, perhaps life elsewhere could evolve under conditions very different from our own. On Proxima b, any potential life might never experience a blue sky. It could exist beneath a permanent crimson glow cast by its red dwarf star. Plants, if they exist at all, might use wavelengths of light very different from those used by vegetation on Earth. Microbial ecosystems could thrive beneath the surface, protected from stellar radiation by layers of rock or ice. Entire oceans might exist below frozen crusts, warmed by heat escaping from the planet's interior. For now, these possibilities remain scientific hypotheses. But they are grounded in what we already know about physics, chemistry, and biology. Beyond telescopes, engineers are already imagining a future in which humanity sends spacecraft to another star. One of the most ambitious concepts is breakthrough starshot. Rather than launching a single massive spacecraft, the project proposes sending thousands of tiny probes propelled by powerful Earth-based lasers. Accelerated to a significant fraction of the speed of light, These miniature explorers could potentially reach the Proxima Centauri system within a few decades. If such a mission succeeds, humanity would receive its first close-up images of a planet orbiting another star. For the first time in history, we would no longer rely entirely on distant observations. We would explore another solar system directly. That achievement would mark one of the greatest milestones in human history. Yet even if Proxima b ultimately proves uninhabitable, its importance will not diminish. Every nearby exoplanet teaches astronomers something new. Each discovery improves computer models of planetary evolution. Each observation helps scientists understand how common Earth-like worlds may truly be throughout the Milky Way. And every answer brings new questions. How many rocky planets exist around nearby stars? How many possess stable atmospheres? How many have liquid water? And among those countless worlds, could one already be home to life? Perhaps the greatest lesson from Proxima b is not about a single planet. It is about perspective. Only a generation ago, planets beyond our solar system were almost entirely hypothetical. Today, astronomers have confirmed thousands of them. With every improvement in telescope technology, those distant points of light become real places with landscapes, climates, atmospheres, and histories of their own. The James Webb Space Telescope has opened a remarkable new chapter in that journey.